Okay, so now we're going to talk some about the general theory of DEs. We're going to be looking at linear algebra and differential equations, like the connection between the two of them, because it's going to kind of come in handy to help us think through solutions to higher order differential equations, linear and nonlinear. So we're going to start out, and we're going to first talk about the derivative, and consequently linear operators are going to end up being linear transformations. So if you remember, to be a linear transformation, we need two requirements. We need that t of u plus v, okay, has to equal t of u plus t of v, and also that t of cu is going to equal c t of u, okay, for c belonging to some field. Okay, that's either going to be C for us or R, and U and V belonging to a vector space V. Okay, in the case of our linear operators, we're going to have L, our linear operator, is going to go from CKI to CKI. Okay, and so what that's going to look like then, we're just going to talk about the derivative. So just taking a derivative, for example. So if I take my transformation L, okay, and let's just imagine we'll define L of U as equaling just D, or excuse me, Ly as equaling just dy. So just taking the derivative, because that's the most simple way of thinking about this. And so that's going to be just y prime. And if we take another one, we'll take L and we'll call it LV, okay, another function v, and so dv is just going to equal v prime, okay? If I take L of y plus v, okay, just as the derivative, just defining it as the derivative, this is going to actually equal y plus v prime. But if you remember your rules about derivatives from calculus, this is just equal to y prime plus v prime, okay? And that thus is going to equal L of v plus L of y plus L of v. All right. So the derivative, essentially, what we know is that we can actually take, we can either add first and then take the derivative, or take the derivative and add afterwards. Okay. First requirement of a linear transformation. The second one is going to be the scalar multiples, and you might be able to figure that out. So we got L of c of, and we'll use y, and that's going to equal cy prime, which we know is cy prime. Okay, because you could take the scalar out and then take the derivative of y afterwards, everything's fine. Remember, those rules of derivatives actually allow us to do that. And so this is then C L of y. Okay, so L, this particular linear operator, is a linear transformation. Okay. Now, all we're going to do with our linear operators is we're just going to multiply by functions. Okay, multiply by basically scalar functions, right? Functions of x only, so they operate as just functions, right? And we'll add those functions together, and we're going to multiply them by scalars. So consequently, we can imagine that if you just take a general one, okay, a general function, not just our function of like just the derivative, any general linear operator, it's going to be a linear transformation, okay? And it's going to, like, the proof of that would actually extend from this exactly, from the qualities or characteristics of the derivative. And this is going to be actually really kind of handy for us, because it's going to allow us to think through some important aspects of differential equations. So now our linear transformations we can establish that we have linear transformations here for our differential equations. Now we need some key vocabulary that's going to help us out to kind of explore this a little bit more. We start out with non-homogeneous and homogeneous DEs, and this is just a reminder from our first chapter. So the differential equation Ly equals 0 is called homogeneous, and the differential equation Ly equals f of x, where f of x is not the constant 0, is called non-homogeneous. So basically, you've got a differential equation, you set it equal to 0, you're going to have a homogeneous differential equation, and if you have our linear operator set to a non-zero function, it's going to be called non-homogeneous. So now what we want to do, now that we've got this kind of vocabulary, is we now want to talk about the kernel of L. So we've got the linear transformation, we've got this idea of a homogeneous differential equation. So the kernel of L is going to be the set of all solutions to the homogeneous differential equation Ly equals 0. And this makes sense because remember the kernel of L is the set of all vectors v such that t of v equals 0 if we have a linear transformation. L is a linear transformation. Y is what we call the vectors that we are actually operating on from the linear transformation. And so if we set it equal to 0, we should end up finding a kernel. That's it. That's the idea. We want to find the kernel. So it's going to be the set of all solutions to Ly equals 0. So let's take a look at an example. So let's go out and find the kernel of L, and we'll let L equal d minus 3x squared. And so what I'm going to do now is I'm going to say, okay, well, Ly, okay, is going to equal dy minus 3x squared y, and that's going to set, I'm going to set that equal to 0. So then dy is going to equal 3x squared y, okay, and this is the derivative of y. Actually, yeah, this is the derivative of y, so this is going to be y prime, or rather, dy dx is going to equal 3x squared y. What you should notice there is that that's separable. So I've got a separable differential equation. So I'm going to get dy over y is going to equal 3x squared dx. I'll take the integral of both sides. Dy over y equal to the integral of 3x squared dx. So that's the natural log of the absolute value of y is going to equal x cubed plus c. Raise both sides to e power. I'm going to get y equals ce to the x cubed. Okay. Remember that e to the c is just a constant. Using our rules of powers, we can just bring it over to the front. And that's the set of all vectors that are all equations that are in the kernel of y. Let's take a look at another example. Let's suppose that we want to find the kernel. We'll find Ker of L. And we're going to have that L equals x squared d plus x. So what we'll do now is we're going to take x squared dy plus xy equals 0. I'm going to change dy into a derivative, so this is going to give me x squared y prime plus xy equals 0. And I'm going to notice that this is first order linear. Okay, so first order linear differential equation, and so I can use my first order linear properties. It's first order linear and, yeah, exactly, first order linear. So I'll divide through by x squared. So I got y prime plus, and this is x over x squared, so that's 1 over xy equals 0. And so, consequently, I'll now need my integrating factor I of x, and that'll be e to the 1 over x dx, or e to the integral of 1 over x dx, which is e to the ln of x, which equals x. So, this gives me x, y prime, then is going to equal 0 times x, which is just equal to 0. Take the derivative of both sides. Derivative of xy prime dx equals the integral of 0 dx. So that means that xy is going to equal some constant, and thus y equals c over x. And this is the set of all elements that are in the kernel of L. Okay. Now, a couple things to notice here. One is that we've got a constant, right? So what we're looking at here is the things that are in the kernel. There's actually an infinite number of functions, but they're all of this form, right? Ce to the x cubed, or c over x, okay? And so consequently, we've got an infinite number, but they're all of a particular form. We call them a family of functions. If you remember, they're called a family of functions. And basically, anything that's in this family of functions is going to give you back the 0 vector. Choose one, try it out. Put 2 over x. See what happens when you plug it into L. So we'll try it out. We want to find L of 2 over x. This is going to end up equaling x squared times the derivative of 2 over x. So 2 over x prime plus x times 2 over x. Okay. This, the derivative of 2 over x is negative 2 over x squared. So this equals x squared times negative 2 over x squared plus x times 2 over x, which equals -2 plus 2, which equals 0. Okay? So we can actually see, yeah, 2 over x is in fact in that kernel. Pick any value for c, and you're going to see that it's in the kernel. By the way, to show that a vector is in fact in the kernel, what you do is you plug it into the function and see if you get 0 back. That's kind of the idea. So now we want to talk a little bit now about the solution space of the nth order linear, nth order homogeneous differential equation. So we're going to be looking only at homogeneous ones at the moment. We'll look at other ones more depth in just a little bit. But so the set of all the solutions to the regular nth order homogeneous differential equation, and this is the differential equation, okay? Notice y to the n is the order of the derivative. So those are derivatives. It's an nth derivative, not an nth power. So just remember that that's the case. And what you've got is you've got basically functions of x only in front of each one of your derivatives of y, and set equal to 0. And then this is the important part. It's on an interval of I is a vector space of dimension n. So if I have an nth order differential equation, what I know is that I'm going to end up with a vector space of dimension n. And what that's going to do is that's going to tell me how many solutions I'm going to have inside of my solution space. Okay, basically like it's the number of vectors. So if you kind of think about it, you remember that if we have a basis for a dim n vector space, right? Then that actually means that we're going to have n vectors, right? Not only n vectors, but they're going to be n linearly independent vectors. And we're going to talk about that in just a little bit, okay? So we're going to have n linearly independent vectors. And so consequently, what that tells me is that I'm going to need for an nth dimensional homogeneous DE, I will need n solutions. So all of our techniques that we're going to be looking at inside of this section are all going to generate for us, for the homogeneous differential equation, they're going to generate n solutions, n linearly independent solutions. And we're going to talk about how do you know they're linearly independent in just a little bit, okay? But that's the first thing we want to start with. We're like, okay, I get it. If I have a second order differential equation, I'm looking for 2 solutions, okay? Or if I have a fourth order one, I'm going to be looking for 4 of them. Yes, and I want to make sure that they're linearly independent. So the methods that we're going to be using are going to be able to make sure that we end up with linearly independent solutions. All right, so let's take a look at an example. Let's suppose that we want to determine all of the solutions to the differential equation y double prime minus 2y prime minus 15y equals 0 of the form y equals e to the rx, where r is a constant. So this is actually going to become something that's very, very handy for us inside of our next section, where we start solving or finding the solutions to homogeneous differential equations with constant coefficients. They're going to all look like this. But let's just kind of think about what it is that we're doing here, all right, and what we need to do in order to kind of solve this problem, and then also to think about how does that relate to the solution space to our differential equations. So notice, right, this is a second order DE, okay? Second order DE. And so since we have a second order DE, we're looking for 2 solutions. All right, we're going to be looking for 2 different solutions to this, 2 linearly independent solutions. And they're all going to be of the form y equals e to the rx in this case. So I'm going to come in and I'm going to say, okay, well, if that's the case, I'm going to actually plug in e to the rx, or I'm going to find L of e to the rx, and that's going to equal e to the rx double prime minus 2 e to the rx prime minus 15 e to the rx, and I want to set that equal to 0. Okay, so then I'm going to set that equal to 0. And that's just, we want to find out whether or not this is a solution to this differential equation. How do you do that? You do that by plugging the function into the differential equation, right? That's how you verify something's a solution. So we're going to use that method here. Now the second derivative of e to the rx, so I'm going to take e to the rx, d dx of e to the rx is going to equal r e to the rx, and then d squared, dx squared of e to the rx is thus going to equal r squared e to the rx. You're going to see me do that a lot, actually. That just keeps my derivatives straight. So now this gives me r squared e to the rx minus 2r e to the rx minus 15 e to the rx equals 0. So if I factor out e to the rx, I get e to the rx times r squared minus 2r minus 15, and that equals 0. E to the rx will never equal 0. So that means that r squared minus 2r minus 15 has to equal 0, which is good news because we want to figure out what r is anyways, right? We want to find r. So what that means is that I get a polynomial here. I'm going to get r minus 3, or excuse me, r minus 5 times r plus 3 equals 0. So r equals 5, or r equals negative 3. Now I just noticed that I can plug those into my functions. So this gives me e to the 5x, rather ce to the 5x. So y1 will be equal to ce to the 5x. And that allows me to have any constant that I want in front. And you can check, we'll see that that's in fact going to be the case. Or y2 is going to equal ce to the negative 3x. Okay? And so those are going to be my solutions. We'll actually prove that these are linearly independent in just a second. Okay? But first, let's just go in and let's confirm that in fact we do have solutions. So I'm just going to let c equal 1. So I'll let c equal 1. So if I do that, then I've got e to the 5x double prime minus 2 e to the 5x minus 15 e to the 5x, e to the 5x prime, by the way, pardon me. And I want to see, does that equal 0, right? Because that's going to actually solve this equation. So e to the 5x double prime is going to be 25e to the 5x minus 2 times, and this is 5e to the 5x minus 15e to the 5x. So that equals 25e to the 5x minus 10e to the 5x minus 15e to the 5x, which equals 0. So yeah, that's the solution. Okay? Put a constant in front of it, you're going to get the same thing occurring. We can actually do that with the constant if we wanted to. Try out e to the negative 3x, e to the negative 3x double prime, minus 2 e to the negative 3x prime, minus 15 e to the negative 3x. And this thus is going to give me 9 e to the negative 3x, okay, plus, this is going to be negative 2 plus negative 3, so plus 6 e to the negative 3x minus 15 e to the negative 3x, and that of course is going to equal 0 as well. So we can see that both of those are in fact solutions to our differential equation. The next question that we want to ask is whether or not these solutions are in fact linearly independent. Because if we have two linearly independent solutions, then what we have is we actually have a basis for the solution space. Okay? So let's actually ask and answer that second question. So in order to answer that question, we're going to go to the Wronskian. So when we talked about determinants, we did talk about the Wronskian. And so the Wronskian, if you remember, it's the determinant of, if we have functions y1 through yn, it'll be the determinant of this matrix. So the matrix is going to start out with y1, our first function, and then we're going to take its derivatives all the way down to the n-1th derivative. Okay, so if I've got n functions, we'll go down to the n-1th derivative, and then we'll do that for y2, and then we'll do that all the way up through yn, which will give us an n by n matrix, and we write it as the Wronskian of y1 to yn. So let's say, for example, we'll take an example because I think that's probably the easiest thing to do. We want to find the Wronskian of e to the 5x e to the negative 3x. So remember, those are the two vectors that we got, or the two equations that we got, or functions that we got as a solution to our earlier problem. So what we'll do is we're going to find the determinant, and we're going to set up the matrix. We're going to have e to the 5x and e to the negative 3x at the top, okay? And then we'll take the derivative of e to the 5x. That's going to end up being 5e to the 5x And we'll take the derivative of e to the negative 3x. So that's going to be negative 3e to the negative 3x. We take its derivative, and we end up with negative 3e to the 2x minus 5e to the 2x, which ends up giving me negative 8e to the 2x. And that's the Wronskian. Okay, so there's going to be the Wronskian of our function, or excuse me, of our set of functions. Let's take a look at another example. So what do we do with that? Actually, let's not look at another example. What do we do with that? What we're going to do with that is we're going to say, okay, well, if the Wronskian of y1 through yn does not equal identically 0 for all x belonging to R, or belonging to our interval, whatever interval that we're looking at, then y1 through yn are linearly independent. So just like our rules for determinants, like if the determinant does not equal 0, then we know that the column vectors of the matrix are in fact linearly independent. Well, in this case, since the Wronskian doesn't equal identically 0, that actually tells me that these functions are linearly independent. Okay? So if I look here, negative 8e to the negative 8e to the 2x, okay, does not equal 0 at all, ever, for all x belonging to R in this case, right? For any of them. So y1 equal to ce to the 5x and y2 equal to e to the negative 3x are linearly independent. So we can actually prove that those two sets are linearly independent. Okay, and there we are. All right. So if the Wronskian doesn't equal 0 for all values of x on the interval, it could equal 1 for one of them or maybe a couple of them, but for all of them, like if there's even just one where it's not equal to identically 0, then what we have is we have a linearly independent set of solution functions. So let's determine if e to the 2x, e to the 4x, and 6e to the 2x plus 3e to the 4x are in fact linearly independent. Let's determine if they are linearly independent. So we're going to find the Wronskian. Find the Wronskian for e to the 2x, e to the 4x, and 6e to the 2x plus 3e to the 4x. By the way, before we even begin, notice that 6e to the 2x plus 3e to the 4x is a linear combination of e to the 2x and e to the 4x. All right? So, albeit we are going to use the Wronskian in order to prove that they're linearly independent, but you could actually say no, they're not. Because what they are, that third vector, or that third equation function there, is in fact a linear combination of the first two. So we can be pretty sure that we're going to end up with identically 0 here. But let's actually take a look at it, see that that's the case right now. So we're going to find the determinant then, and we've got three functions here. So that's going to be e to the 2x, e to the 4x, 6e to the 2x plus 3e to the 4x. Then we'll have 2e to the 2x, 4e to the 4x, and 12e to the 2x plus 12e to the 4x. And then we'll have 4e to the 2x, we'll have 16e to the 4x, and we'll have 24e to the 2x plus 48e to the 4x. We'll take that derivative determinant now, and that'll give me, I'm going to write it down and then I'll go calculate it. It's going to be e to the 2x times 4e to the 4x times 24e to the 2x plus 48e to the 4x minus 16e to the 4x times 12e to the 2x plus 12e to the 4x. And then this is going to be then minus e to the 4x times 2e to the 2x times 24e to the 2x plus 48e to the 4x minus 4e to the 2x times 12e to the 2x plus 12e to the 4x plus, okay, and then finally we're going to get 6e to the 2x plus 3e to the 4x times, and this is going to be 2e to the 2x times 16e to the 4x minus 4e to the 2x times 4e to the 4x. And so what you can do actually is you can plug this into symbolic calculators, whether or not you're looking at Wolfram Alpha, Symbolab, MATLAB. They'll actually go out and find this determinant for you, and that's exactly what I'm going to do right now. And what I get then is I get that this is equal to 0. Exactly like what I thought. Everything else cancels out. It's identically equal to 0. So what that means for me is that e to the 2x, e to the 4x, and 6e to the 2x plus 3e to the 4x are linearly dependent because their Wronskian ends up equaling 0. So now we're going to focus in on non-homogeneous differential equations. And we talked a lot about homogeneous. They're going to become really, really important. They're going to help us to structure vector spaces. But now, what about non-homogeneous ones? Because frequently, in fact, most of the time, we're going to want to be working with non-homogeneous differential equations. So we're going to need a little bit of vocabulary. The first is that we're going to suppose that we have a non-homogeneous DE, Ly equals f of x. So the differential equation Ly equals 0 is going to be called the associated homogeneous differential equation to Ly equals f of x. Okay? So basically, if we pull off f of x, right, and put it to 0, that's going to be our associated homogeneous differential equation. So we get x squared y prime plus 6xy prime minus 3y equals 6 sine x. My associated, right, homogeneous DE, okay, is just going to be x squared y double prime plus 6xy prime minus 3y equals 0. Okay? So we're going to have methods for solving the homogeneous parts, and then we're going to have some methods for finding the non-homogeneous parts. All right? And our next theorem is actually going to be like this key kind of linchpin that we have there. And we talked a little bit about something kind of similar when we were doing differential equations, okay? Or excuse me, when we were doing linear algebra. We're now going to really use this fact a lot as we work with non-homogeneous differential equations, okay? So we're going to introduce first some notation. The first notation is we're going to call something YC, okay? YC stands for the complementary solution. So we got the complementary solution, and what that is that's going to be the solution to the solution to Ly equals 0. So the solution to Ly equals 0 is going to be called YC. Then YP is a particular solution to Ly equals f of x. So it's going to be a particular solution, not necessarily all of them, just one of them, to Ly equals x, all right? Remember, a particular solution is, right, we have an initial condition. We can solve for C. And so consequently, these two things, YC and YP, are going to be actually really important for us, because it turns out that the solution to all non-homogeneous differential equations are of the form YC plus YP. So we can actually state that the solution to all Ly equals f, so all non-homogeneous differential equations, will be of the form y equals YC plus YP, where YC is the solution to Ly equals 0, and YP is just one particular solution to Ly equals f of x. Okay? Super important here, because that's how we're actually going to structure our solutions to all of our differential equations. Is we're going to first, we're at least going to think about the solution to the homogeneous the associated homogeneous differential equation, and then we're going to add to that solution, right, a particular solution. Okay? So let's take a look at an example. Let's suppose we want to show that yp equals 2e to the 6x is a solution to y double prime minus 2y prime minus 15y equals 18e to the 6x. So let's first show that yp is in fact that solution that we're looking for. So I'm going to need a second derivative. So I've got 2e to the 6x. The first derivative is going to be 12e to the 6x. And the second derivative is going to be 72e to the 6x. That's then going to be, so we're going to have 72e to the 6x minus 2 times 12e to the 6x minus 15 times 2e to the 6x. That's going to equal 72e to the 6x minus 24e to the 6x minus 30e to the 6x, which equals 18e to the 6x. Okay? So check, yp is a solution to this non-homogeneous differential equation. Now notice our associated homogeneous DE is y double prime minus 2y prime minus 15y equals 0. Now we actually already found the complementary solution. And so remember that our solutions here, we had a solution space of e to the 5, e to the 5x and e to the negative 3x. So that was my complementary solution, if you remember that. So the solutions are y1 equals ce to the 5x and y2 equals so the c1 and c2 e to the negative 3x. So what we'll do is we combine those two into yc. yc ends up equaling then c1e to the 5x plus c2 e to the negative 3x. And then what we need to do in order to find our solution, our y solution, the whole solution is yc plus yp. So that ends up equaling c1e to the 5x plus c2e to the negative 3x plus our solution 2e to the 6x. So notice that in order to find our overall solution, we added yc plus yp. yc plus yp, and that gave me the solution to the entire non-homogeneous differential equation. Okay? So what we're going to do, like as we continue to work, is we'll find the solution to the associated, to Ly equals 0, and a yp, and then add them together. That's what we're going to basically do throughout a significant portion of this entire chapter. So just as an overview for this lesson, what we talked about was thinking about the differential equation and the solutions to differential equations as vector spaces. And that helps us to structure the solutions to differential equations, to think about how many that we're actually looking for, and to kind of think about what does it mean for the solutions to be actually different in some way. And so when we're looking for, we're trying to construct a basis for the solution space for a homogeneous differential equation, remember that if you have an nth order differential equation, that is the highest derivative is a derivative of n, then we're looking for n linearly independent solutions. Okay, n linearly independent solutions. Our methods are going to give us linearly independent solutions. But if you need to figure out whether or not they actually are, you're going to utilize the Wronskian. Okay, so if I have n linearly independent solutions, by the Wronskian, I have a basis for the solution space to the homogeneous differential equation. And then the other big thing that we actually talked about here, amongst other things, is that if I have a non-homogeneous differential equation, then what I'm going to do is I'm actually going to find the solution to the associated homogeneous differential equation, called my complementary function, and then I'm going to add that to a particular solution. So if I just have one particular solution, then I'm going to be actually able to add that to the solution to the homogeneous part, and that's going to give me the solution to my non-homogeneous part. And what you're going to see is that our methods are going to be twofold. One is we're going to find the solution to the homogeneous part, the associated homogeneous differential equation, that complementary function, and then we'll have another method that will allow us to find the solution to the particular part. Okay? And so that kind of wraps up what it is that we talked about inside of this section on the general theory of DEs.